Hello everyone, I'm Ashwin. I, along with my colleagues Desh and Kerr, will explain the system submission from Johns Hopkins University. The team members are Ashish, Desh, me, Kerr, Bar, Matthew, Piotr, Paula, Shinji, and Sanjeev. We participated both in track 1 and track 2. The speech recognition model that we used in both tracks are the same. So we will present our track 2 system. This slide shows the pipeline that we've used for the track 2 system. It consists of 4 stages. The first speech enhancement stage involves dereverberation and denoising. The second stage involves extracting the speaker segments and in turn has 3 components: speech activity detection, diarization, and overlap assignment. My colleague Desh will explain this. There is a speech enhancement stage after we get the speaker segments to extract the signal corresponding to the target speaker. Finally, there is the speech recognition stage, which my colleague Kerr will explain. Like I said earlier, there are 2 speech enhancement stages, and I'll explain them. The first pre-processing step we performed was weighted prediction error-based dereverberation. We used the online multi-channel version, and we fixed the filter order to be at 10 and prediction delay at 3. We subsequently used a delay and some beamformer to denoise the signal. Now, alternative to using a delay and some beamformer, we also tried using a neural beamformer. Here, we trained a neural network to separate speech mixtures from noise. The network was trained with data simulated from Voxeler and noises extracted from the CHiME 6 data. Although the enhanced output sounded perceptually better, it didn't improve the final ASR performance as shown in the table. So this was not incorporated in our final system. We also tried other ideas. We tried using blind source separation using 2 methods, IVA and TASNet. This again did not give us good results, so it was not included in our final system. Coming to the speech enhancement, after we extract the speaker segments, we use guided source separation proposed by Paderborn University during the CHiME 5 challenge. Like the original proposal for track 1, we used the ground truth annotations, and for track 2, we gave annotations obtained from the diarization. This slide shows the importance of having an overlap assignment component while extracting speaker segments. As shown in the table, we can get significant improvements in the div data where the overlap ratio is more. Given the enhanced output of GSS, we perform multi-view decoding. We try 2 types of fusion, early and late fusion. Highlighted are the results obtained using single array GSS. Early fusion can be performed by incorporating all arrays while beamforming. And here we see a significant improvement. We can also perform late fusion by doing a lattice combination. Here we use the lattices from single array GSS and also multi-array GSS. We choose the lattice weights in such a way the multi-array GSS lattice gets more weight. Here we can see further improvement in performance. To summarize the takeaways from the speech enhancement, we get good improvements using guided source separation, and it is very sensitive to the diarization output in track 2. We can also get further improvements by combining early and late fusions. Now I'll hand over to my colleague Desh.
Hello everyone, I'm Desh and I'll present the speech activity detection and speaker diarization components of our system. For the baseline that we built for speech activity detection, we had a TDNN stats-based architecture. We didn't change the architecture for the submission system. Instead, we performed some multi-array extensions to this system. So to start with the baseline SAD, we have different arrays where the channels in each arrays are beamformed, and finally we just choose one of the arrays at random, namely U06, for the downstream segmentation. However, as you can see here, U06 is not necessarily the best selection. U03 or U04 perform quite a bit better than U06. So we ask ourselves, can we do better than beamforming for channel combination? And number 2, can we do better than random array selection? To answer the first question, we tried channel level posterior fusion by removing the beamforming with a posterior fusion over all the channels. We find that this does not really work as well. So in particular, channel level posterior mean is slightly worse than beamforming, and channel level posterior max is almost the same as beamforming, as you can see in the U06 here. However, this comes at the cost of 4 times more compute, so we stick to beamforming. Next, we try posterior fusion for array combination, and this works quite a bit well. In particular, you can see there's a 34% improvement when we use posterior max, and most of this gain comes from improvement in list speech. This directly affects diarization error and word error rates downstream. So the takeaways from SAD are that beamforming is better than channel level posterior fusion, but array level posterior fusion is good, and it's better than selecting any array randomly. Next, we move on to the diarization. For the baseline system, we built a well-known pipeline consisting of an X-vector extractor with 0.75 second shift, followed by PLDA scoring and clustering. First, we investigate how the better SAD that we have improves diarization, and we find that it improves the DER by almost 4%. Next, we have 2 questions from the baseline system. First, can we use multi-array information instead of just picking U06? And next, how can we handle overlapping speaker segments since the baseline ignored this completely? So to answer the first question, we first tried using Dover, but we couldn't really get it to work for us. So instead, we tried PLDA score fusion inspired by the posterior fusion in our SAD. And we find that especially when we use PLDA score max, we get 1% improvement. This is a little underwhelming though. So we ask whether we can get more improvement by breaking the segments into more pieces. And this was inspired from a paper from BUT for their second Die Hard challenge, where they used 0.25 second shift instead of the regular 0.75 seconds. So we tried this, and we find that this improves the DER by about 1% over the regular 0.75 second shift. Next, to handle overlaps, we have this pipeline where we take the output of the output RTTM from the diarization system, and the overlap detected output from an LSTM based overlap detector and assign overlap to it. For the overlap assignment, we propose 2 methods. The first is a heuristic based approach where the overlap segments are just assigned to speakers which come before and after it. And second is the VBHMM based resegmentation, which is also overlap aware. And this was proposed first in the paper that we cite here. Our heuristic based approach gives about 1.7% improvement, whereas using VBHMM gives almost 7% improvement. So this is really significant. So the takeaways from this part are that multi-array PLDA fusion helps when you use smaller segments instead of 0.75 second shifts. And overlap assignment is significant when we are using VBHMM based resegmentation, which is overlap aware. And this would also ultimately help in downstream word error rates as well, since we are detecting speakers more accurately. I now hand it over to Kurt to take it from here. Thank you.
Hi, this is Kay. I'll talk about the acoustic model part in our system and then summarize the talk. Our acoustic models are HMM, GMM, DN model with Let's MMI training objective. We train the HMM GMM model on the combined closed talk and the enhanced far-field data. Speech perturbation is defaultly used in Let's MMI training stage. So basically, this is a standard pipeline, except for the overlap part. I'll talk about that in details later. For model architecture, so in our system, the TDNF model is used as the baseline. And on top of that, we try different model architectures, including the 3. This SE means self-attention. So we observed that CNTDNF gave us the best performance. Here, we show the CNTD model in this figure. This is a 6-layer CN layers as the feature extractor. And on top of that, we have 16 TDNF layers. For the input part, except for I vector and filter backs, we have this extra overlap feature appended on top of that. This overlap feature is a one-bit feature vector, which indicates whether the segment is overlapped or not. Training data selection. In CHiME 6, we have several data sets. And first column is the closed-talk data. And the second is the simulated data. And third, array means the far-field data. The last two are two augmentation techniques on top of the far-field data. The first is beamform, and second is GSS, guided source separation. The idea is from this paper. Basically, we observed that using a beamform and GSS outperform the raw far-field and the simulated data a lot. There's a difference between the first row and the last row here. And this combination gave us the best performance and also give us the smallest data set so that we can train the model very fast. Here are some experiment results for the overlap feature. As I mentioned, we train neural network with this appended overlap feature. So we found that appending the overlap feature to a vector and neural network gives the best performance. Compared with no overlap feature appended, we observe a small water reduction here. These are the results on the track 1. For track 2, we'll do more experiments. Neural language model in this study are a forward and backward LSTM. Each is a 2-layer project LSTM. The backward LSTM is trained on transcriptions that are reversed on sentence level. We basically do a 2-stage proof lattice scoring. Stage 1 is forward LSTM, and on top of that, we use the backward LSTM to do another lattice scoring. We use Kali for both neural language model training and rescoring. Here are the step-by-step improvements for track 1. Compared with the baseline TDNF model, the CN-TDNF architecture gives a slightly good improvement here. And proper data augmentation, training data selection gives significant improvement here. Overlap feature helps a little bit. And both language model rescoring and lattice combination on model level gives modest gains. So overall, we observe 22.2 modal reduction on depth and 21.1 modal reduction on eval. Here are the track 2's results. We don't have overlap feature here. And I want to mention that this lattice combination is on array level, not on model level. So we only have one acoustic model for track 2. As Dave talked before, PLDA fusion gives us good gains here. And GSS, as Ashwin talked before, gives significant improvement here. And then combine these different techniques together. Overall, we observe 90.6 modal reduction on depth and 30.4 on eval. Here are the summary of our findings in building this system. First, for front-end, we found that GSS performance improved with improvement in diarization error rate. For SAD, multi-ring posterior fusion improves the results significantly. For diarization, we had 2 findings. Multi-ring PLDA scar fusion shows small improvement in diarization error rate, and the VB-HMM-based overlap assignment shows large diarization gain and the small water error gain. For acoustic model, we found out deep CN-TDNF model is the effective architecture, and proper enhancement helps a lot. For example, the beamform and GSS outperform the raw far-field data and simulated data a lot as a data augmentation technique. Language model part, neural language model scoring give us modest modal reduction. So in general, I want to mention all systems are built in Kali. We will release the recipes in the future. We hope this can benefit people working on CHiME also. So that's my talk. Thank you.